Okay, welcome back. We're going to go ahead and continue where we left off last time. So far we've looked at the idea of naming chemical compounds or chemical nomenclature. We have come up with a systematic way of naming special type of compounds, such as binary compounds, for example, or compound that includes polyatomic ions and so on and so forth. The next thing that we're going to do is going to look at the description of compounds in a little bit more detail and hopefully try to bring it into the real life situation. In real life, we cannot really work with individual molecules or individual formula units. So for example, when we write down a chemical formula, like for example, H2O for water or NaCl for sodium chloride, we are really telling you certain specific information. We're really telling you the formula itself tells us how many of the atoms of each of the constituents there are in that compound itself. So we're really using a simple model that will allow us to kind of visualize what goes into making a particular chemical compound. So if it is a molecule that are basically connected covalently, we will then have a molecular formula. If it is an ionic compound like this, we then have a formula unit that tells us how these ions will then repeat themselves throughout a macroscopic crystal, for example. So here we have some really interesting information in that I can now relate the number of atoms of each type to each other, as well as to the formula unit in general. So if I look at this, I can say that, well, for every one molecule of water, I actually have 2 atoms of hydrogen and 1 atom of oxygen. So these guys basically make up this particular formula unit. And that's kind of nice because now it allows us to now make a connection between these individual constituent parts, as well as with the whole unit. So for example, if I, let's say for example, have 1,000 H2O molecules. If I have 1,000 H2O molecules, I might ask you, how many atoms of hydrogen are there in this particular sample, or how many oxygen atoms, and so on and so forth. And if we want to answer those questions, it's very simple in that we can just use the idea of unit conversions all over again, as long as we have a connection between all the things that I'm interested in. So just like before, we would start this particular inquiry in the following way. So if I had a 1,000 water molecule, my question might be how many atoms of hydrogen are there and how many atoms of oxygen there are. So we always start off with, again, what is given to us. We come down here, we look at the 1,000 H2O. Don't forget, again, in this case, specifically let you know that this is the number of molecules I'm dealing with. Then just like before, we create a unit conversion factor. I want to get rid of H2O molecules. I want to end up with H atoms. So the question is, what is the connection between the number of atoms and, oh, here it is. I have 2 atoms of hydrogen for every 1 molecule of H2O in general. So that means I can put 2 there, put a 1 there. So that means that this cancels out. That will then give me a total of 2,000 hydrogen atoms. That seems really simplistic, but as it turns out, we can use the same idea later on for more complex type of situations. So we want to use the simplest idea, it's going to help us to understand the process, then later on we can apply it to more complicated situations. In the same way, to find the number of oxygen, you use 1,000 H2O molecules. And then, in this case, of course, the ratio now will be different. In this case, I have now 1 oxygen atom per 1 water molecule. So when this works out, I now have 1,000 oxygen atoms in my original sample. And this can be done for any chemical compound. As long as you know the chemical formula, and by looking at the individual subscript, you can then find the ratios between the individual elements and the compound itself, as well as between 2 different elements as well. So for example, something a little bit more interesting, a little bit more complex, might look something like this. So let's use something a little bit more interesting. Let's use a ionic compound. So let's say we have something like barium nitrate. So you call, if I give you a formula name, barium nitrate, how will we go ahead and figure out what the chemical formula is? So in this case, again, write down a metal, in this case ionic compound, write down the ionic charge on this barium. So if you look on the periodic table, you find that barium will form a +2 charge. The nitrate, again, you can look up in the your table that's given to you. And nitrate would have the chemical formula NO3 with a -1 charge. So knowing the individual ionic components, you can now put them together in the formula. So just like we did before, barium nitrate crossing over. This gives me a 1 subscript here, and then together, this is now a 2 subscript over here. So this is now the chemical formula, okay, for barium nitrate. So this is the formula unit. Okay. The question then is, of course, in this case, what are the contributions for each of the elements towards this chemical formula unit? So I can ask, well, if I have, let's say, a certain number, in this case, a nice number would be asking either in numbers of atoms, okay, or number of moles. And a lot of times when we have to count in the large quantities, the number of mole unit will always be very convenient. So let's assume that I have 2 moles of barium nitrate. Okay, so the question then be, how many, let's say, in this case, how many moles, okay, of barium do I have? How many moles of nitrogen do I have? And how many moles of oxygen would I have? So again, you can see that this is consisted of 3 different elements here. So doing it just like we did before, the key is to make sure you keep track of things properly. So in this case, we start off with 2 moles of barium nitrate, multiply this now by some sort of conversion factor, and so I want to get rid of moles of BaNO3 2 here first. So for every 1 mole of barium nitrate, the question is how many moles of barium do I have? Well, you look at the subscript for that particular element. In this case, the subscript is going to be 1, so I have 1 mole of barium. So that goes away. So again, making sure that you cancel out the proper things, and when you work this out, you end up with 2 moles of barium. So that's pretty easy. Okay? That's pretty obvious. The next one, of course, is take a look at the next one. The next one, I'm going to go ahead and find the number of nitrogen. So I start off again, 2 moles of barium nitrate, NO3, 2. In this case now, I have for every 1 mole of barium nitrate. The question is, how many moles of in this case, I want nitrogen, so put nitrogen over here. Nitrogen do I have? This is to be very careful, because in this case, notice the whole thing here is in a parentheses, and there is a subject to tell you how many times to double things up or triple things up or whatever it might be. So if I have a single nitrogen in the polyatomic ion, and there are 2 such polyatomic ions, that means this subscript must then multiply by this subscript in here to give you the total. So this is really 1 times 2, or 2 moles of nitrogen, or 2 atoms of nitrogen, if you look at it in terms of the individual atom units. So in this case now, when you work this out, you end up now with 4 moles of nitrogen in your barium nitrate. Okay? The third one, of course, is now going to be for oxygen. So we do the same thing. 2 moles of barium nitrate. Okay? Multiplier here now is, again, for every 1 mole. So it looks like a lot of writing, but this is actually really good to make sure that you see where things are clearly, so that later on when things get a little bit more complicated, you don't get lost in the confusion. In this case, the question, of course, now is how many moles of oxygen do I have? So as per what we did before, since there are 3 oxygen for every 1 of the polyatomic ions, and there are 2 such ions, now you take 2 times 3, giving you a total of 6 oxygen. Okay? Or in other words, 6 moles of oxygen for every 1 mole of barium nitrate. So when you work this out, this then gives you a total of 12 moles of oxygen. Okay? So each of these then will give you the corresponding number of moles. So if you check, okay, notice that the subscript really, again, is what tells you the amount of each of these particular elements there are in that particular formula unit. So make sure that you practice doing this in your homework as well as worksheets and so on. All right, so once we have this, what's the next step? Well, as it turns out, once we have the formula, we're able to now look at the percentage or the fraction of each element in terms of its contribution to the whole of your molecule or your formula unit. The next step, of course, is to bring it to reality. Most of the time when we work with these chemical compounds, we're not going to be able to look at a single molecule or a single formula unit. We're not going to be able to look at just 1 atom of barium to every 2 atoms of nitrogen to every 6 atoms of oxygen and so on and so forth. We're not going to be able to work with them individually like that. Most of the time we're going to have to work with macroscopic quantities. And in order for us to investigate macroscopic quantities, we need to be able to make measurements. And the measurement that we're going to be making in investigating the properties of these guys are going to be, of course, mass measurements. And so we need to somehow be able to relate mass measurements with the chemical formulas and see the connection between the two. So let's take a look at how that happens. Let's do a very simple, substance first, just to kind of see things. Let's go back to our really, really popular substance of water. So imagine I have H2O, So let's, in this case, if I compare the individual contributions of oxygen to hydrogen, we see that, as we said before, there's 2 hydrogen atoms for every 1 oxygen atom in making this particular substance. So the hydrogen and to oxygen is always going to be a 2-to-1 ratio. So I only have twice as much hydrogen as I have oxygen, but this is only in terms of counting. So I'm counting atoms. Or if I look at a larger bulk counting, I could also talk about the fact that there's going to be 2 moles of hydrogen atoms, for every 1 mole of oxygen atoms. So even if I count in larger units, I still have the same 2-to-1 ratio in terms of counting by particles. However, if I were to ask, well, what about the mass contribution? If I were to look at the mass of hydrogen and compare it to the mass of oxygen, would that also be in a 2-to-1 ratio? Would I have twice as much mass of hydrogen as I would have oxygen in that water? And the answer obviously is going to be no. As it turns out, that's not going to be the case. So how do we make that connection? How do we know what the contributions are between these 2 parts to the whole in terms of mass? So in doing that, we're going to be looking for something that's going to be quite useful, and this is going to be called the mass percent composition. The mass percent composition basically tells us the composition of a particular substance, some sort of compound with some sort of formula, in relation to the constituent parts. What is the percent of each part that contributes to the whole, so to speak? And so in the case of looking at counting, we can just use whole number ratios that are very easy. In the case of looking at mass percent composition, because we're measuring things out now, it might be easier to look at something that's more specific. And more specific means that we can use this idea of percentage. Percentage basically is looking at the number of parts out of 100 parts, or basically the fraction out of 1, for example. So that allows us to kind of break things up very nicely and be able to visualize what's going on if we deviate everything. So we have a certain mass for a substance and we call it 100%, then what percentage of each part sums up to that 100%. That's what we're going to be looking at. So we're going to look at the mass percent composition. And the mass percent composition is fairly straightforward. We already know the count ratio. Really, we just need to convert now from a count to a mass. And that's something that we have done in the previous chapter. So this is where now the payoff is. So let's see what that looks like. So to find the mass percent composition of something, the first thing we need to do is find the mass of the substance itself. We can look at it in terms of a molar mass, for example, or a specific sample. Most of the time, you may not know how big a sample is, so it is always good to kind of think about, well, what if we look at a theoretical sample? One theoretical sample would be, let's say, for example, 1 mole of a particular substance. That makes life a lot easier. Or, in this case, if I'm looking at mass, maybe 100 grams would be a nice number to use, because that would then fit in with the idea of percent really nicely. So that's the idea. So the first thing you do is first find the mass of your total substance, and then look at the part contribution. So let's take a look. Let's say I have this idea of 1 individual sample. I have water over here. So my question is, what is the mass of this particular sample? Well, there's 2 ways I'm going to calculate mass. Once I can actually look at the individual atomic masses to find the molecule mass, the molecular mass, or I can look at what happens when I look at a whole mole of this sample, and then use that as my reference. Either way, what you'll find is that the numbers will always come out to be the same. The units may be a little bit different, so let's see what I mean by that. So let's take a look. In terms of the contribution that goes into making this up, there is going to be 2 hydrogen, for every 1 oxygen, So knowing that, I can now ask myself, if I look at this as individual atoms, for example, what would then be the mass of 2 atoms of hydrogen? Well, I can go ahead and use the atomic mass. In this case, the atomic mass of hydrogen is going to be 1 atomic mass unit. So I'm just going to go ahead and round it up to 1, just to make sure that we focus in on the idea and not worry so much about the numbers themselves. Later on, when you do the calculations yourself, you will actually put the actual numerical value in here based on what you get off the periodic table. So later on, you actually put that in there with the whole 1 point, for example, 00793 AMU instead of just 1. But this makes it a little bit easier to kind of keep track of. Then we look at the oxygen. For the oxygen, it's going to have 1, and the oxygen will have a mass when you round it up to about 16 atomic mass units. So that gives you now 2 times 1 giving you 2 AMU. Okay, and this now gives you 16 AMU. So for a total of, when you add 2 hydrogen to 1 oxygen, you now have a total mass of 18 AMU, okay, for the mass of your water molecule. So this is by looking at the atomic mass unit for individual atoms. You could also think in terms of a molar mass. The molar mass of a substance basically is the mass of 1 mole of that substance. So in terms of molar mass, the idea here is, instead of looking at 2 atoms of hydrogen, I can ask, well, what is the mass of 2 moles of hydrogen? If that's the case, then I would have the moles of hydrogen would have a mass of 1 gram per mole of hydrogen. Okay? 1 gram per mole. In terms of oxygen, okay, it would have a mass of 16 grams per mole. So now you can kind of see what I mean by the numbers being exactly the same. You take the same number off the periodic table, the only thing that's different is you attach a different unit to it. So this is now going to be grams per mole. So to work this out, you have 2 grams per mole. In this case now, of course, this is going to be hydrogen. This is now going to be 16 grams per mole. This is now going to be oxygen over here. Okay? Whereas over here, this is now, of course, the mass for hydrogen up here. This is mass for oxygen over here. This is now the mass for your water molecule. So in the same way, if I add these guys up now, I end up with 18 grams per mole. This is now my H2O. So in other words, if I had 1 mole of water, I would expect to get 18 grams worth of it. And so interestingly enough, this idea of the molar mass again is a connection between mass and mole of a substance. So you kind of think in terms of equivalent is that 1 mole of H2O is now equivalent to 18 grams of H2O. Okay? So that allows you to kind of go back and forth between masses and the counts in terms of moles of substances and so on. So once I have this, okay, how do I then go ahead and figure out the mass percentage of each of the contributions? So I want to basically be able to come up with so many percent of hydrogen and so many percent of oxygen is in each, okay, is in this particular compound here. Well, it's real easy. You take the part divided by the whole. That's how you get your percentage, right? So this is the part that contributes to this whole. You can take this ratio now as your percentage. So that means over here I can take, okay, if that's the case, I can take 2 AMU divided by 18 AMU times, in this case, 100%. Okay, so when you do this, this will give you a fractional value. But when you multiply by 100%, that'll then give you a percentage. And if you work this out, you end up with 11.1%, okay, hydrogen by mass. When you do the next one, this is now 16 AMU divided by 18 AMU times 100%. Okay, notice in this case that the AMU units cancel out, it doesn't matter. So that your final, okay, percentage doesn't have any units aside from that percentage sign there. When you work this one out, you find that this comes out to 88.9%. Okay? So as it turns out, if you look at the ratio between the masses of hydrogen to oxygen, rather than being a 2-to-1 ratio of hydrogen to oxygen, you now have practically an 8-to-1 ratio of oxygen to hydrogen. You have 8 times more oxygen by mass in the water than you do hydrogen. So a very, very different percentage or a very different ratio. So make sure you understand that there's 2 different ways of comparing things. Don't get them mixed up. This is a mass percent, this is a count comparison. Okay? So this allows you to do it. Now, whether I use these numbers or these units doesn't really matter. If I go over here, I will then have grams per mole, and the units goes away, and then the numbers will be exactly the same. So this allows you to calculate, okay, the percentage of each contribution, okay, to your particular whole. This is an easy one, right? Because we all know H2O is easy. So let's make things a little bit more interesting and do another example using a little more complex system. But the whole idea is still the same, right? You're looking at the contribution for each component and then comparing that component to the whole afterwards. So let's see if we can do this one more time and see what happens. So let's try something a little more interesting. Let's go back to that barium nitrate that we had before, okay? So we have barium nitrate, okay? And I want to find out the mass percentage of each of these 3 contributions. So in other words, I want to find out the percentage of barium, percentage of nitrogen, percentage of oxygen for each of these, okay, substances. So to do that, I start off with breaking them up into, okay, the individual elements. I know that I have barium over here, okay? And then now in terms of nitrogen, how many nitrogen do we have here? Well, for each of the formula units, I now have 2 nitrogen okay? Because again, multiply the subscripts out from the inside to the outside. Then of course, 3 times 2 now gives me 6 oxygen, right? So once I have that, I can now go ahead and bring in the masses. So if you look at this from your periodic table, you find that for barium, okay, right over here, this is roughly 137.33. You can use grams per mole, or you can use AMU, doesn't really matter. Then for your nitrogen, 2 times now, okay, nitrogen will have a value of 14 point, let's go ahead and round it up to 14 grams per mole, okay. Then over here, for oxygen, you now have 6 times, again, we'll round it off to 16, okay, grams per mole, equal to. So if you go ahead and work all this out together, you're gonna have 16 times 6, added to 14 times 2, added to 137.33, and you end up with a total of, over here, okay, 261.33 grams per mole. This comes up to be 137.33. This comes up to be 28 grams per mole. Grams per mole. 96 grams per mole. Okay, so you add it up, you have your 261.33 grams per mole. Now once you have the total, the next step, of course, is to look at the individual contributions. So to get to your barium percentage, you take your barium over here, divide by this. So for barium, 137.33 grams per mole, divided by 261.33 grams per mole. So again, parts over the whole. Then of course, the next thing, of course, also multiply by 100%. So if you work that out, you end up with, okay, times 137.3, okay, about 52.6, okay, percent roughly. Okay, 52.6% roughly. And if you go to the next one now for your nitrogen, you have roughly 28 grams per mole, divided by 261.33 grams per mole. Okay, that'll give you 8 divided by, let's see, 261.33, and that'll give you roughly 10.7%. Okay. And finally, for your oxygen, you now have 96 grams per mole, divided by 261.33 grams per mole, times 100%. Okay, 96 divided by 261.33, I'll give you roughly 36.7%. So this is now for barium, nitrogen, and oxygen. So these numbers can now be carried over. Now, interestingly enough, of course, if you add all this together, what do you expect to find? Hopefully, you get back, okay, 100%. So you have 52.6 plus 10.7 plus 36.7. That'll give you 100%. Sometimes you may not get exactly 100%. That's because of the fact that there's going to be some round-off error along the way. So you might get a little bit over, a little bit under, depending on, again, where that round-off occurs. Okay, but most of the time, you should get pretty darn close, right back to 100%. So this allows us now to kind of figure out the mass contribution of each of the individual components that makes up a particular substance. Now the question is, why do we even bother doing that? What's good with that? Well, the good thing about this is that once we understand how to find this, okay, if we can actually somehow determine the mass percent contribution, mass percent composition of these different substances, we can actually now work backwards to find out what the chemical formula for that substance might be. And that's where, for example, a lot of time when you watch shows like CSI, for example, any kind of crime scene investigation, if somehow they find some evidence at a crime scene and they have some sort of chemical compound that they don't know what it is, and they want to make sure they figure out what it is, you don't go and start tasting it and see what it tastes like, right? The whole idea is that you want to be able to do some chemical analysis. And one of the things you can do is, of course, you can break it apart using some sort of process that will allow you to then break the substance into the individual components, collect all the individual elements that are in there, and then figure out how much of each element you have in there. Based on that, you can come up with a profile of this mass percent contribution. So, for example, sometimes when you see the situations on TV or in a movie, you take that substance, grind it up, put it in the centrifuge, shake it up, and then you put it in this fancy machine, which is a mass spectrometer, that allow them to basically separate according to the masses. based on how massive the particles are, as dictated by the different atomic masses for different elements, to separate into different locations that can be then detected and measured. And so you get a printout, okay, on the computer where you see these little spikes that comes up like this. Depending on the position of the spike, you can then identify the individual elements, and how high the spike is will determine the percentage of that particular substance, okay, that element in that particular substance. And with that, we can now figure out, okay, what that substance might be. Now, of course, it sounds very simple. As it turns out, it's pretty complex, okay? But let's kind of take an idea of how it is that we can actually achieve this, okay, knowing this mass percent composition. So let's, again, do a very simple example as a model to help us visualize this process, and then we'll go into more detail in terms of how we would do it for more complex cases. So the first thing let's do is let's take a look at what happens when we have water, for example. Let's assume that I'm taking chemistry for the first time and I have no exposure to chemical compounds and the formulas at all. So I know what water is, I use it all the time, but I have no idea what the chemical formula for water is going to be. So my question is, what is water made out of? What is the chemical formula for water? I don't know at this point. So let's say that I start off by looking at a certain amount of water. So here I have a model that I'm using. So I have a certain amount of water in here, and I find that I can now find the macroscopic property of mass associated with this sample of water. So in here I have 108 grams of water, okay? And so what I'm going to do is I'm going to assume that I can now undergo a chemical process where I go in there and I break that water up into its individual components. In other words, into hydrogen gas and oxygen gas. You can actually do this using a battery, for example. Okay? If you use a battery, you can actually use the electrical process in the battery to separate, okay, hydrogen and oxygen and collect them as individual gases. So let's assume that I'm able to do that. So let's say I have to start 108 grams of water. Okay? So my starting point, I have 108 grams of water. What I'm going to do is I'm going to go ahead and break this up into its component pieces. So obviously I'm going to have hydrogen on one side, oxygen on the other. I'm going to find out how much I have of each. And let's assume that I actually are successful in doing that. And here I have now all the hydrogen has been separated. And I find that I end up with 12 grams of hydrogen. Okay? So 12 grams of hydrogen right over here is what I would collect, okay, from that process. And over here, I have now all the oxygen piled up, and I have now measured it, and this has 96 grams of oxygen. So that's going to put that over here, 96 grams of oxygen. So the idea is that when I have the masses, okay, don't forget the unit, grams, okay, although they tell me the ratio of the mass of one substance to the other, they don't tell me, okay, the formula itself, because remember, the chemical formula, okay, those subscripts tell you the number of atoms of each type or the number of moles of each type. So before I can make any kind of a guess as to what those subscripts are, I have to now change grams of substance to moles of substance that allows me to now compare. What I really want is I want to find out how many moles of hydrogen there are, okay, for every given mole of oxygen that I have in the water molecule itself. And so that's the goal. In order to do that, I now have to make a conversion between grams and moles. And that's something I said that we have learned how to do before. So in this first step, of course, to convert grams to moles, I start off with 12 grams of hydrogen. Okay, so I want to get rid of grams of hydrogen, put that on the bottom. I'm going to end up with moles of hydrogen, put that on top. So I know that for every 1 gram of hydrogen, 1 mole of hydrogen, there's going to be what? 1 gram of hydrogen. Okay, so once I have that, I can now go ahead and do the calculation. Again, I just use the rounded off number. In your case, if you were to do this for a problem, you should put in the whole number, okay, the actual number based on the periodic table. So when I work this out, I now have 12 moles of hydrogen. 12 moles of hydrogen. On the other side, if I look at the oxygen now, how much oxygen do I actually have here? So I do the same thing. For oxygen, I now take 96 grams of oxygen, and then I want to get rid of grams of oxygen, end up with moles of oxygen. For 1 mole of oxygen, I know that I have now 16 grams of oxygen. So now grams of oxygen cancels out, okay? And I end up with now moles of oxygen. And if you work that out, you end up with basically 6 moles of oxygen. Okay? So now I have converted from a mass of my substances into moles of substances. That means in my original sample, okay, of 108 grams of water, I had 12 moles of hydrogen in there and 6 moles of oxygen in there. The next step, of course, now I can go ahead and compare, okay, those numbers in a ratio. So I'd say, okay, what if now I want to go ahead and compare the number of moles of hydrogen to the number of moles of oxygen? What would that comparison be like? Well, in this case, I have 12 moles of hydrogen for every 6 moles of oxygen. So that's the comparison. In other words, I'm really asking, okay, how much bigger or how much more of the hydrogen do I have compared to my oxygen? So when I take the amount of hydrogen, moles of hydrogen, compare with the moles of oxygen by dividing it by the smaller number, I now have the number of times hydrogen is bigger than oxygen by. So it's 12 times 6, that will give you 2 moles of hydrogen for every 1 mole of oxygen. So a 12 to 6 ratio is the same as a 2 to 1 ratio if I simplify it. So this tells me, oh wow, for every 1 mole of oxygen, I can expect to now have 2 moles of hydrogen. I can now use this information to say, well, if my formula for hydrogen, oxygen together form water looks like this, there are going to be subscripts here that tells me that ratio of number of moles of one to the other. I can see that, okay, for every 2 moles of hydrogen, I can have 1 mole of oxygen. This would then be my chemical formula for water. Okay? So this allows you to kind of work backwards, knowing the masses of the substances, in other words, knowing the mass percent composition, you can work backwards to figure out what the formula is. This particular way of doing it, most of it is done, of course, in the laboratory. Okay, these are called empirical formulas because you rely on experimental results to actually get to these numbers here. They basically represent the lowest whole number ratios between the individual components of that particular compound. Okay, so that's just kind of one example of how we can do this in a very simple situation. So we're going to go ahead and stop here for now. When we come back the next time, we're going to look at how to look for a systematic way of doing this for any scenario so that even if the problem is fairly complicated, you can still use the same idea and still allow us to figure out what the empirical formula is going to be. And then we're also going to talk about something called molecular formula, and then that will wrap up this particular chapter for chapter 6. Okay, until next time, take care.